So I'm going to do a quick presentation on baking tonight, and I'm going to share my screen, and let me know when you can see it.
You can see it.
All right. So my name is Chester, like I said before. I have links to the website of Bacon and the GitHub. I'll post the slides afterward. So Bacon was designed to be a background code checker, but that's not what I use it for. I use it for background code checking. Yep, I do that. I also use it to restart applications that I'm working on. I use it to store frequently used commands. So like per project, I have commands like to do certain things, like different little scripts. I probably just put those scripts into Bacon, so I don't have to like remember where I put them or what the commands are. And then I'll use it for give me notifications on long-running commands. So like some builds take a little while to run, and I put them to run in the background, and I don't have a screen on them. But when it's done, Bacon gives me a nice little notification noise. So that I really appreciate that. And then it simplifies compiler-driven refactoring. So when you make a change, you have all these places to go update. Bacon just keeps on popping up the next error at the top, so you can just control-click on that and keep on jumping to the next error to fix all of those. But why should people use Bacon? Because these are the reasons I use Bacon. I can't really speak for other people, but I have two screens, and the error messages that show up in the IDE are sometimes a bit too small. So I like having Bacon just bring up the full error message on the other screen for me, because it pulls up the whole error message, which can, sometimes take up more than half the screen, depending on what error it is. And then it also sorts the feedback from the compiler, so the errors get put before the warnings. Otherwise, you end up sometimes with warnings at the top, and you have to scroll to find where your errors are and that kind of thing. And then it scales your feedback to the size of your terminal. So if you have a small terminal window, it'll adjust to match that. And if you have a big terminal window, then again, like on my second screen, I'll get a full screen with my error messages. And then it has an option by default. It will not keep on just like showing the errors as they come up. It'll wait until it has all of them, and it'll just present the sorted view of them. But I personally like it to nothing, so that's optional. You can just change that if you like. So this is the default output from an example program that I wrote, and this is what Clippy would show. So if you just run cargo Clippy, then you'd have a warning first, then an error, then another warning, and it would just put them in, order that it meets them. If you do the same thing here, so you see the error, you see the error highlighted here, and if you do the same thing in Bacon, then it numbers them and it puts the error first and puts the warnings after it. So the error shows up at the top, and then if I took the same thing and I put it in a small window, then we'll just put the error at the top still, and then it just fits what it can fit there. So this is what I have in terms of slides. We're going to do a quick demo of Bacon. And I wrote this little application that likes to drink beer. And we're going to pull up a small terminal at the bottom here. And we're going to do Bacon run. Bacon run. And that's going to tell Bacon to run this program. When you do the default Bacon run, it doesn't stop the program if you make changes. So like if I change 99 bottles of beer on the wall, I put, let's say, another comma, I save, it doesn't actually restart the program by default. So if you want it to actually restart, then there's another version of run, Bacon run long, and that one is designed for more long-running tasks. So if you make a change while it's running, like now I want to take out the extra comma, and I save, it'll automatically restart it for me. And then if your program also spawns sub-processes, then you can just use a different command to also kill the sub-processes as well. Otherwise, they by default won't get stopped. Then this will let me close with just queue, so I can queue to quit. But then if you have a lot of jobs, it sometimes gets a little bit tricky to try and remember all of them. So you can ask Bacon to list the jobs for you, and it'll list out all the jobs you have saved for this project. So this list will include both your global jobs, which you can specify at the preferences level at the top, like in your default that works for all projects, as well as you can define them per job, per project. All right, and then we're going to put this back to run, and we're going to run it this time with a little bit of a different version that has some errors and warnings in there. All right, so let's put this to run, but it can't run because, well, this is wrong. So 1 minus 2 is a negative number, and U64 doesn't support negative numbers. So I just take this out, and that'll be fine. But the thing I wanted to show is that this automatically scales to the size of the window. So if I resize the window down, it'll put it here, and I can just scroll in the window to see any other errors if I had to scroll. And then if I save this now it'll actually start running, but it'll still show the warning here. And if I wanted to see the clippy warnings, because that was just the default cargo warnings, compiler warnings. So if I wanted clippy warnings as well, then I could run clippy all, and it'll run clippy and show me all the different warnings for clippy in this mode here. Now, it also does test really nicely, in my opinion. It gives you a green light if the test pass, all tests pass, or you can also specify the shortcut keys yourself, but by default it has like T for, actually if you press H, it gives you a list of what the shortcut keys are, which includes the ones that you define. So if I also define more shortcut keys, then it would also show me my shortcut keys in this list. So I can just press T to see the jobs, to run the test job. And then my test takes 5 seconds to run because I put a delay in there so that we can see the refreshing. So now it's showing this test here. And let's say I made a fix to one of them. Let's say I fix this one. And then I save. It doesn't automatically refresh right away because that kind of creates noise while you're working on other things. So it gives you the option to, by default, wait until it's completed before it will refresh the screen. So it shows you a pink bar up here. It says that it's computing, but it won't actually refresh. Yeah. If I do fix all the errors, probably by just not checking for them, and I save, then it will show green instead of red. Right, green up here. Because it still have warnings, it'll have a yellow. If I go to fix the warnings, what are my warnings? Oh, unused variables. And maybe I just comment you out and then it can go faster. Oh, there we go. But you can customize the jobs. So by default, it comes up with, it works without having to do any configuration. But if you wanted to, you could say beacon init, and that will create a configuration file for you with the default jobs. You can delete the jobs and they'll still work because they're included by default. But you could use this now to override the jobs. So for example, the test, I like seeing the test run faster. So I could say background equals false. So it won't run in the background anymore. Now it'll run in the foreground. And I could have left that open because it will automatically reload once the configuration gets changed. So let's say if this was out like how it was before, then this would be the long version of the test. Let's put that to 3 seconds instead of 5. Oh, that's not the file. So by default, it'll still do this. And if I go into here and I change it, so where is it? Test. Yeah, here it is. So if I take out background false, it'll run right away. So it will run even before the test is it'll start showing the results right away, even if it's not finished yet. Oh, don't forget that test not at the bottom of this. So if I put this back, error, it's still running, but it's still that this one failed already. And then when it's done, it'll show you the nice, pretty sorted output with the panic message and everything in the test. I think in terms of time, I'm going to stop here. But basically, all these jobs, you can also configure them at the global level so that they work for all projects, and then you can override them per project. So if you have a job at the global level, and you have a job with the same name at the project level, that will override it by default. So you can specify all the different settings as well at the global level. So it's just like a priority list. The closer to the project it is, the more higher priority is. So you can have settings at the top of the configuration file. Like you could have some settings like a default job up here, different environment variables to set. You can also set background equals false. So if you always like that to be false, you could put that there. And if you want it for all projects, then you just do code. Beacon dash prefs will give you the path to the preferences as well as create it if it doesn't exist yet. And then you can put the preferences in here, and that works across all the projects. You can set the sound volume and those different things. I don't think it compiles. It does. No, I don't think the sound is not enabled by default because not probably everyone doesn't want that. But you can just compile the sound in with the compile flag. We had to disable. Well, I say we. They also had to disable it to support. I think one of the platforms I was having trouble compiling in the different sound things. One of the packages. Sorry. And down here is where you'd set your shortcut keys. You can set whatever shortcut keys you want and that kind of thing. So I'm going to leave it here because I think I'm out of time. All right. Thank you very much. Any questions, though? Anybody had questions quickly?
Yeah, how easy is this to set up with like other languages?
Right now, it supports a few languages already. Analyzers. So they were starting to they've been adding as people need, but it's mostly as needed. It's not the author himself doesn't use it for all these other languages. So when people have needs, they basically ask and he just adds it in for them. But it has first class support for us because, well, that's what he uses it for.
Right.
As well, he's very responsive on GitHub. So if you wanted to add one yourself, it's actually not that hard. The code's there and it's pretty easy, in my opinion.
Interesting. Okay.
And there's a cookbook on the website with little tips and tricks for different things you can do, including how to run jobs from the command line. So you can add additional jobs from the command line thing. And these take precedence over the jobs in the file. So you could overwrite a job in the file like this. So you just copy this, just paste, and then you could run the job there. And it put the little hello, which was what was in the job.
Okay.
Oh, I forgot to mention that. Well, I think I did say about the sound, but you can set the sound so that if you have them running in the background, like for example, cargo format, then you can set it if it fails to make a noise, because normally I don't need to hear about cargo format or look at it at all. But when I have it running in the background, I want to know if it fails, because sometimes cargo format fails when you use a lot of macros. And then it just stops working, and that's kind of annoying. But the reason I have to run it in the background is because I use the line wrapping feature, and that's nightly only, but my project is stable. So I have to run it on a separate version of the compiler, and Beacon allows me to do that in the background. Okay, I don't take too much time from Aaron. I'm not sure how long his presentation is.
Yeah, Daniel, did you have something?
Yeah, do you have a quick demo that you could show off with the next test integration?
I've never used NextSet integration, but I know that one does work because people use it, but I don't. I could look into it, but I have never used it before myself.
Fair enough. Thank you.
All right, sorry. I guess if you have more questions after Aaron, then we can probably double back.
All right, sounds good. We will move over to Aaron then. Just give me a second here. I need to adjust the microphone.
It's good.
Just press the button on the back there.
This one?
Yeah, that one. Make sure it's not muted.
Oh, I see.
Yeah.
Yeah.
And then point it towards you. Don't tilt it towards you. It's a side adjust.
Oh, sorry.
Yeah, so like that. That's fine.
All right. Can folks hear me?
Yes.
All right. Yeah, sure. Just sharing my screen here. Of course, Firefox says I have to rejoin. All right, let's see if this works this time. Nice. Okay. Yeah, so I thought I'd just give a little bit of an intro to performance in Rust. Of course, there's many reasons why we might want to use Rust, and performance often comes up as a critical one. Rust famously is a systems programming language, but it is also much safer, of course, than C, C++. And C and C++ are some of the core languages still today because they have high performance and are suitable for systems programming, in addition to all the other things that people might use them for. Rust, of course, breaking into that realm, performance is still very critical. It's got a lot of other features too that it makes it look a lot higher level than, well, certainly C and somewhat C++ as well. So it's kind of nice to take a step back and say, okay, well, first of all, like, where are we with performance in terms of how fast are we really? And then if something isn't as fast as I would really like it to be, what are some of the tools and technologies that I can use to start looking into my program to say, okay, well, why is it fast or why is it slow? So I'll just start with, I've got just a couple scripts here for example. So code-wise, everything you see here tonight is going to be very simple, just so that we don't spend too much time on exactly why something is good or bad. But here I've just got a Python function. Assume that this is something that's business critical for me, or for some reason it's expensive and I want to make sure this runs quickly. So we've got your recursive Fibonacci definition, and it's really just I pass it a number and then I'm recursively calling the fib n minus 1 and minus 2 to get me a Fibonacci number. So if I run this, it is functional, but it's not super fast. So you can see from the output here, if I'm calculating fib 20, it took 523 microseconds, give or take, which is not really that great. I mean, for such a simple function, this recursive version has a number of problems with it, and it's one of the classical, like, introduce people to, pathological recursion, where this really blows up because the two different invocations of the nested Fibonacci are completely unrelated to each other. So if I choose fib 20 on the outside, I compute fib 19 and fib 18, but they're unrelated, meaning that all the work that I do for computing fib 18 gets duplicated for fib 19, and then vice versa all the way down the stack. So this actually goes and calls the Fibonacci function here hundreds of times, and so it's not very fast. But if I start with a simple definition like this, one thing that people do, this would be very easy to write in Rust. So perhaps let's do exactly that. But at the same time, we care a little bit about how fast is this running, and I mean, you can see that in Python. I'm just using this time it function from the standard library. It's just a very simple way of benchmarking. It's not necessarily that accurate, and because it's just a single run, it does run it a bunch of times, but it doesn't compute any statistics. I just get an average number for all of this. So I can start with my Fibonacci, and so in Rust, just quickly, this is what the same function would look like. Again, very simple. We're just using match statement, and we're still doing the recursive stuff. It's not good, but how much better can we make it? And one thing that I wanted to introduce first of all is that if you have something that is very critical to what you want to do, very often, you want to have a benchmark. I'm just going to comment out some of the ones we'll look at in a moment. But we've got this Fibonacci recursive benchmark, and it introduces the first tool that I'd like to mention, which is Criterion. So Criterion is a benchmarking library for Rust, and it's considered pretty high quality. It's very easy to use, just like most other things. So you can add Criterion to your project. So if I look at the cargo toml here, you can make it a dev dependency. So for a regular build, you don't have to build Criterion. You can just keep it for your development workflow, which is great. And then you can define multiple benchmarks. So you'll notice that the double square brackets here in their toml files means that you can define as many of these as you want. I'm just going to define one, call it fib bench, and the harness false thing, we don't need to worry about too much. It's just some additional things that you can attach to your run. And if I have this, and you'll notice that I put this in a benches subfolder, which it looks for by default. And after some boilerplate at the top, just make sure that you've got your basic definitions, and I've got my different Fibonacci's that we'll go through just quickly that I'm also importing. You can define a benchmark just as a function. It takes one of these criterion objects, which is your overall benchmarking tool. So this is where I guess most of the magic happens. And then you can call a method on this criterion object that's bench function. And bench function is actually going to run this a bunch of times, kind of similar to the time it that I showed at the beginning. And it will have a name that we can refer to this later. And you give it a closure for whatever you want your test to be, your benchmarking test. And this can be pretty much anything. It's all Rust code after all. So I gave it this fib recursive, which was this one. So I just imported it from this location, and we're going to call it. Now you'll notice I'm still using 20, but I've got this weird black box thing in here. So this is one of the classical caveats of benchmarking when you've got a compiled language. So Rust, as we all know, has many awesome compiler optimizations that show up all over the place, which generally is great. But when we're trying to benchmark something, what I really don't want to have happen is the compiler be really smart and say, oh, well, you're only passing me 20, and maybe I can even figure out what the return value for 20 is, and you're just going to call this, a million times or something like that, and I'm just going to immediately return the same value because I can detect that this is in a loop. We don't want that. So what the black box is, it's a way that you can hide from the compiler what the input to this function is. And this is only really useful for benchmarking, but it basically means that on every run, we can guarantee that, for at least from the compiler's perspective, this is a brand new run of my fib recursive function. And certainly if you've ever tried profiling in C++ or C, you can accidentally run into these cases where your benchmark runs much faster than it really should. But with all of that said, how do I run it? Well, because everybody knows that we've got cargo. Cargo is great. Cargo comes with a cargo bench command. That's what I'm going to use. There's also a cargo criterion subcommand that you can also install that just sets up some stuff by default for you a little bit differently. And so what's happening, I just expand this slightly. So you can see it compiles your stuff. So in this case, I have compiled it already once. So this was relatively fast. It also runs your tests, which is, I don't have any tests here, but it's useful because, of course, you always want to make sure that in addition to your benchmarks passing, that your code still works the way it's supposed to be. So functional correctness and code speed is in some ways orthogonal, but you need to make sure that both are correct when you're doing benchmarking. So I ran this, and you can see it tells you a little bit that it ran this fib recursive 20. It collected 100 samples in an estimated 5 seconds. So this is configured by default to run for 5 seconds. And it actually called my function 505,000 times. So that's how you read this. So it basically ran through its benchmark test suite 100 times for a total of 505,000 calls of my particular function. And this ran in, we'll call it 10 microseconds. Just as a reminder, when we ran the Python one, it was like 500. So we're 50 times faster just by choosing a different programming language. So far, Rust is absolutely living up to its reputation as a fast language. And you can see it gives you some more stats too. So it gives you your mins, max, and it also tells you about outliers, which can be very important, especially if you have a more complicated function. You may have cases where you sample inputs and some other things where highlighting some of your outliers can also tell you if your system is busy, if it's a valid test, but it can also give you insight into whether you've got pathological corner cases with performance. Okay, so this is great, but even 9 microseconds actually seems fairly long. It's not very good. And if you've seen the Fibonacci examples before, you'll know that with the explosion of the number of calls, doing Fibonacci recursively, while it's a great learning tool, is a horrible way of doing it in practice. So the next one I'll introduce is we have a benchmark, and we want to make our benchmark faster. And Criterion makes it really easy to just add new benchmarks. So close the Python one here. I'll close our bad one. But you can see I can basically write as many function benchmarks as I want here, and it'll become part of the suite as I run it. So the next one, I've got an iterative version of the same thing. So instead of calling a recursive function, I can basically just keep track in 2 variables what the previous 2 values were, and then just iteratively go through this list and add. So you can see if I want fib 20, there's basically going to be 18 iterations of this for loop because I've already initialized the first 2 values here, and I can return that. So how good is that? I've cut off a lot of the extra calls to Fibonacci, so I don't have the overhead of a function call, and I'm not redoing a bunch of work. So I can rerun this again, and again, it's going to do its warm up here, and it's going to run, about 500,000 times, and I kept the first one here. I'll probably comment out for the further runs just because it's by far the slowest. But you can immediately see that with this iterative version, so I went from 10 microseconds to 6 nanoseconds. So I got roughly 2,000 times faster just by making this relatively small change. And you can also see it that now it went through in 5 seconds, 845 million iterations. And 5 nanoseconds is getting better, but this calculation isn't particularly complicated. So I think it might be possible to do better. So in this case, just to go through the iterative quickly one more time. So we've got a for loop. So if I do 20 as an input, then I know that I've got to do a few additions here, and I'm saving some stuff in these variables, and it's not a big function, but again, it's doing a little bit of work that in principle, maybe I could save it. And one thing that is worth noting about Fibonacci, and this is in general, I think, how you need to approach a lot of performance-related problems, is you want to look at it and you want to say, okay, well, what are the key characteristics of my problem? So I'm passing in a U64 here. And what's notable about Fibonacci sequence in this particular case is that in a 64-bit value, you can only fit the first 92 iterations of the Fibonacci sequence, and then you've run out of space. And so you can actually go and define something like a lookup table, where you've just defined a function, and I have a constant version of this as well. I'll show in a sec, where it's really as simple as I'm just looking up this value from a table, because I can statically calculate these, and it just becomes part of my my binary. So our lookup, and maybe I'll run the constants just so that we see them all at the same time. But oops, what did I do? I'm missing an open parentheses. Oh. So just giving it a little bit of time to warm up. You'll actually see, I haven't really changed anything, but just because of noise on my system here, you can see that it is fluctuating by a couple percent, and it will also tell you when it's fluctuating. Do you have an improvement? Do you have a regression? You can change all these thresholds and stuff too. So Criterion has good documentation. You can tell it this is the threshold I want you to care about, and you can add this to your like CI and GitHub or wherever. But just to show, so moving to a lookup now, we've gone down to 680 picoseconds. So we've actually done a roughly another factor of 10 improvement in speed. So now we can actually perform this function in 7.4 billion iterations in 5 seconds. So using benchmarking, and this is a micro benchmarking example, you can narrow in on a function that might be critical to your application, and then you can actively figure out, like, is what I'm trying better or worse, and you can fiddle around with your code, and on a run by run basis, it'll show you how well you did. And also, if you want to see some more information, all of the output, and they're changing the defaults here, so some of the warnings says that the HTML will no longer be there unless I turn on a feature in the future or I use the Cargo Criterion runner. But just for now, what we can see is it also gives you, for people that love stats, if I do the iterative one, for example, it'll actually give you a page where it'll show you things like, based off of the number of iteration runs, like how long this took. And if you're actually serious about performance, these are good numbers to start digging into. So first of all, you can see your rough distribution here visually, but also you can see that roughly around iteration 6 million or so, it started getting a lot noisier. So something started on my system. It could be that, you know, I'm sharing my screen with you guys. Could be something else running, that some of this is a little bit suspect, because we know that this should run in fairly constant time, and I'm not changing the value on a per run basis, so it should basically be the same always. So if I were looking into this as a like an actual work project, I would say, okay, why is my test looking like maybe it's becoming invalid here? So focusing on stuff, Criterion is really great, but there's another problem, which probably a lot of people are already wondering about, is how do I know if I have a problem, and if so, where is that in maybe like a larger code base? So I have not a large code base here, but just something that's a tiny bit more representative, which is a very simple, this is basically hello world using an Axum service. So I've got a tiny Axum service here that basically I'm listening, and I've got a handler that responds with hello world. So I'm just gonna go. Okay, so I've got my my handler running like this. And if I do a hello world, or if I do a request to this, then you can see curl is just dumping back. You know, I returned hello world, and I've got some number. So not to give it away, but you know, what am I doing to get this number? Oh, I've got a bad Fibonacci here. But let's say we don't know this. Like let's say this was like a call to an authentication agent, or you know, anything else. This takes time in my request, and I want to make sure that my requests are running, you know, as quickly as possible. And of course, the bad fib here, I've just repeated it for this page. This is my, you know, bad recursive example that we just saw was really slow. So again, imagine this is a much larger code base, and I don't really know what's going on here yet. But we're about to discover that this is not a great Fibonacci. So how could I do that? So one of the first things you can do is there's lots of tools. So Criterion is a micro benchmarking tool. Another tool that you could use in this case, because it's a request response. Like I've got a little service here. I'll just run this for say 3 seconds. So I've got a tool called OHA, but there's also Hyperfine. There's also a whole bunch of them that are service-based, and there's a lot of tools out there for benchmarking various use cases. So there's a fancy little text output that goes along with a tool like OHA, but all this is really doing is the same as the curl request, but timing everything. So first of all, I can take a look at request stats. So again, if you are a person that's writing services, you'll often find that you care about things like latency and your throughput and things like that. So, you can see that basic stats like how much data am I typically responding to a request, how much am I actually writing back, how many requests did I serve in a particular time, gives you response time histograms, some basic things like that. And again, if you're looking at things like latency or your write throughput, maybe this is where you start to say, is this good or bad? But let's say this is bad. Let's say we think we can do better. We're not really sure why this is slow. So how can we look at this and try to figure out what's running slowly? So I'll introduce, this will probably be the last tool that I introduce before we just do questions and I wrap this up here. But I'm going to introduce flame graphs. So a flame graph is actually a visualization that's really useful to see where your program is spending its time. And there's many different types of flame graphs, but I'm just going to relaunch this with Cargo Flame Graph, and I have to use root. Okay, so there's a tracing tool that's now running in the background here, and I'm just gonna rerun my service request. I'm gonna run it for just maybe a couple more seconds to get more data. So the particular tool that is running right now is called Cargo Flame Graph, which is a nice wrapper around whatever your system's sampling profiler is. So if you're on Mac OS or you're on Windows, that's a program called dtrace. If you're on Linux, it's a different program called perf. I mostly know the perf variants, but one of the things that's really nice, of course, about the Rust environment is that people have gone way out of their way to make sure these things work on multiple platforms. So I can do the exact same Cargo Flame Graph on a Linux machine, and it will work just fine. And so if I open this flame graph, you get this SVG visualization that looks like this. So if you've never seen a visualization like this, what you're looking at here is on the horizontal axis is an approximation of time. What it actually is the number of samples, which might be a little bit small, but it says there were 29,774 samples, which represents 100% of the samples in this case. Some differences between time and samples is that if your program is sleeping, you often won't see any samples. Certainly in dtrace, you don't. There are ways that you can say, show me the sleeping samples and stuff as well, like times that I'm idle, times that I'm waiting for a request response, things like that. But in this case, I'm just doing sort of the basic like CPU busy sampling. And most of this is wrapper like Tokyo runtime. You can see, so Tokyo, this is a async program, so it is running async, and so it's got the Tokyo runtime kind of at the bottom that's managing my whole program. And then I've got some Axum related stuff here, but if you actually look up, I can see handler, which starts here. This is my handler, and on the horizontal axis, I can see the amount of time something took. So some of these little towers, and when you're debugging like this, performance, you usually look at wide towers. So these ones are hyper stuff. I don't directly control that, so I'll ignore them. But if I look at this tower, I can see that there's this function from hello service, which is what I called this program, bad fib. And I can click on it, and I can see that it then scales everything. So you can look at really narrow parts of the peak as well. But I can see I have this bad fib, and bad fib is calling bad fib a whole bunch more times, and it sort of escapes off into the top while being really expensive. And if I hover over this, I can see at the bottom that it's roughly 38% of my runtime here. That's really not great. And because of that, and I've determined that because of some business reason or something, my service is already not fast enough, I could say, the bad fib is really the problem here. So I could change my response. I was kind of an example where you could also show with some extra clones and stuff that were superfluous, but maybe I'll just skip right to. Let's imagine for the moment that this was something I could completely optimize away. I could say run the flame graph again, and I could run my benchmarking tool again, and it finishes. And I open my flame graph again, and now I can see that my tower actually is either one of these really, really thin things now, or has completely disappeared. I may not have any samples in it because just serving HTTP requests is pretty expensive compared to just formatting a single string. So I've managed to completely eliminate the thing that I was trying to eliminate. Of course, this is a toy example, but in real life, you would go through, and if the Fibonacci function were really important to you, that's when you would narrow it down. You'd look at the criterion, you'd probably make a nice little criterion benchmark for this thing, and then you'd start playing around with different ways of making it faster. And just to prove to ourselves that we did make it faster, in our 5 seconds, we now went to 187,000 requests, whereas previously, was this the same one? Or well, it actually looks about the same for requests. I'm actually not sure why that's the case. There may have been some other bottleneck with that tool, but that's quite useful. So I might actually just wrap it up there. So I introduced a couple tools. We had Criterion, which you can fairly easily write new benchmarks for your suite. You can run Cargo Bench to run these benchmarks. And if you define multiple benchmarks, you can do similar things to unit tests. Like you can run just one particular benchmark, for example, if that's what you want to focus on, without changing your code. There's a number of other tools, including dtrace, that are great for generating flame graphs and other things that help you debug your service. And I will wrap it up with that. Thank you.
Great, thank you.
Do you think you could show the flame graph after you remove the extra bad bit? Show that that tower is much more.
Yeah, so I think, so this was, if I just switch back and forth, actually I can.
Did everyone catch that question online? No?
Okay,
No.
so the question was, can I show basically the before and after of what it looked like here? So on the right-hand side is the bad one. So you can kind of see there's like 3 towers here, three major towers, and then kind of a chunk of random noise lower on the left-hand side. And if we look, this tower is a connection pole read head, and this tower is a pole flush. So I had my bad fib, which we just commented out in this case, but in a real example, you'd probably take that function, you'd optimize it away as much as possible. But in this case, what we have left is, on the left-hand side is the one where we've removed it. So we can still see we have the pole read head, and we can see that we have the pole flush. So those are the same 2 towers, and they look relative to each other about the same as they did before. And we still have, a bunch of this looks like little random noise, and that's, Tokayo context stuff, but our bad fib basically completely disappeared. So the internal handler that we're doing now, if I search for it, handler, no, it doesn't even appear here. So we didn't actually sample it because it was fast enough that as a proportion of the runtime, we didn't actually catch it. And maybe if this wasn't clear, so dtrace and perf, they're sampling profilers, meaning that they wake up periodically to figure out exactly at that moment what your program is doing, but they're not watching every single function call. So I think the default is something like 97 hertz or something like that. So it wakes up 97 times per second. And it's a weird number just because they don't want to accidentally be sampling at the same rate as something else is working. So people, tend to like numbers like 10, 100,000, etc. And so if it's a little bit off of that, then it's more likely it'll catch some of these things in the off sample period that might be kind of weird. The other thing to notice here is that the overall width of my graph, these flame graphs, they're always 100%. So when you look at this, and I'm not going to dig into the Axum framework here, but if I still didn't think that my service was fast enough, I would then look at my next widest tower and try to figure out, is there something I can do there? Like, can I optimize something away or remove it the way we did with bad fib? Or is there something inside that code that I need to do, but maybe I can do it faster? Or maybe it's something I can cache, so I can maybe do it once and then reuse a value. Of course, there's many things that you can try to do to optimize your code, but you typically keep looking at whatever the widest thing is in order to keep improving your performance and have the best performance increase per amount of time you spend trying to fix it.
So for the bottom several layers of graph, all of the bars are 100%.
Yeah.
What's the interpretation? Is it like we're always inside, like in a lower scope than whatever the top one is 100%?
Yeah, typically. So the question is, why are all the bars at the bottom roughly the same width, and how do I interpret that? And the way I would interpret that here is that there's program level scope stuff that is probably set up just once at the beginning of the program. We're nested inside those function calls. So I'm hovering over the multi-thread worker in Tokayo here in context run. And so this is the last layer in Tokayo before it starts running your actual code. And actually that may not be true because I see there's a schedule here. So this is the code that would start the scheduler and then starts looking at the tasks. And so, the timeout part of the scheduler for park timeout may represent the time that this is idle as it's running. So my request benchmarker, like there is a period of time when it's kind of idle in between requests. And then the run task with poll, this is calling the actual poll on the future that at least occasionally actually has to handle something. And the handling something is what we see inside these. But yeah, so the stuff at the bottom is basically your context setup. Some tools you'll see like a whole bunch of panic related stuff here too. And that's the Rust standard library, just setting up panic handlers for when stuff goes wrong. And they exist for the whole time of your program running.
I have a question.
Yeah.
So near the start of the talk, when you were doing some explanation about how Criterion works, you showed how some of the test results were sort of slightly inconsistent. You said that was due to noise on your machine.
Yep.
If I'm trying to make many small performance improvements to my program, is there a way to cut down on that noise while testing, or to separate it? Like, how do I make a change that improves performance by 1% that I know that it actually improves something?
Right. So So some of it is that make sure you're make sure you're not doing something like live streaming your desktop to the world while you're doing your benchmarking. So that's part of it, making sure that whatever you're running it on, you've got a relatively quiet machine. It's not doing other things at the same time. Close the other programs, things like that, if you expect it to be pretty narrow. But there's also a lot of like if we look at some of the configuration, I don't know exactly where they have it in their benchmarks, but you can configure all the stuff like the amount of time that you want to run it. It also has many other features, like you can get it to plot like scaling and stuff too. So for like I just showed Fibonacci with one input, but what if I wanted to see how bad that bad case was? And I wanted to go, how long does Fibonacci 1 take up to Fibonacci 20? And I would see a nonlinear scaling. So it lets you configure all those things. If you think it's going to be, only the tiniest change, then, I mean, on the one hand, you can always extend the amount of time you're running it. So you're averaging out over the noise on your machine, and the noise will tend to go to 0 or whatever your baseline level is anyways. So that's one way. Another way is that if it really is too small and you're seeing plus or minus 1% every time, then it could also mean that your optimization isn't making a big enough change for there really to be an improvement in your, because there's always a little bit of non-determinism in your OS.
Okay, thank you. And for the people online, I think that question was about how to reduce the amount of noise in your criterion benchmarks.
Yeah. It might be I haven't had to play with the default settings for criterion that much. I believe there is a TOML file, and then you can also configure it inside your code as you make these benchers. I have to find out where it is. I can probably post the link as part of comments in the README for this repo at the end.
I had a question. First, thanks for the presentation. It was pretty good. So, so the fib, the recursive fib implementation, if you could go there. So, does Rust support tail call elimination?
That's a good question. I don't know for sure off the top of my head. I know there's been a lot of discussion about when tail call optimizations can potentially be inserted, and maybe Jonathan knows a little bit.
I know kind of historically how it's worked. Like LLVM does support tail call optimization, and sometimes it will just kick in automatically, but it's not really like a defined behavior yet, as far as I know. I have seen some rumblings. There's definitely been some work towards trying to support this in some official capacity in certain cases, but in general, I think right now, I don't think the story has changed yet. So it may optimize it, but it's not guaranteed, and the Rust language specification, makes no such guarantees about that.
And even if you do have tail call optimizations, I mean, one of the challenges here is that because these calls are completely independent, most of what makes this a bad performance function is that these are completely redoing the work for both calls. So they're almost the same. And if you were to save state between them, that would already be a huge optimization, which is another way I suppose you could write this function. But switching to an iterative way is effectively the same thing. Yeah, so you would save a little bit of overhead with the actual instructions for the function call, but you're still wasting a lot of work for calculating what the Fibonacci of n-1, and then completely separately redoing all of that work for n-2.
Gotcha. Thanks.
And also, I don't think you can tail call optimize this, right? Because you're having to.
Yeah, they're not in the tail position,
Yeah.
so it wouldn't be tail call optimized because in the AST tree, it's the addition that's actually like tail position. It's an infix operator.
Yeah. Yeah.
Thank you for
Okay.
the presentation. I'm just wondering, have you tried out the a different alternative to Criterion called Diven? I'm not sure exactly how to pronounce it.
Yeah, I've seen it referenced, but I haven't actually tried it. So far, Criterion has met the benchmarking requirements that I've had. So I haven't really gone out to explore the other options. But yeah, there are other options. Criterion is sort of middle-aged, I'd say at this point. It already replaced some earlier unstable benchmarking that I think still exists within Rust, but you have to use unstable. So Criterion moved that into a library. And yeah, there are some newer technologies out there. I don't know their relative merits, but yeah, there's lots of options for tools for sure.
Yeah, personally, I haven't had a chance to try it either, but a couple of things that really interested me about it is that, one, it can measure allocations, which can be an issue, especially in, embedded scenarios or WebAssembly, as well as measuring thread contention as well, which I don't think that Criterion does. Is that correct?
Yeah, that would be more advanced. I don't think it does, but yeah, there's many other tools. Just because you mentioned allocations. Okay, so if I go back and I could do, so with lots of other tracing tools, just copy that. So you can do things like trace the allocations. So, oops, nope. Okay. So what I'm actually doing is I'm manually using that dtrace tool that I said this was based on top of, where I'm actually looking at the malloc calls in this case. So that's one thing that you could look at if you overall found that allocating was a problem and you wanted to look at malloc. There's lots of tools out there for dynamic. The D in the dtrace is dynamic trace, so you can actually get lots of other information here, and there's ways of visualizing this that I don't have set up. But with that particular call, I've now generated basically stack traces for all of the cases where we see malloc being called. So I can see there's the hyperproto. I don't think there's one in my handler now because I commented it out, but I was actually going to show that output like this, if I search for my handler, I can see my malloc, and with some other options I can get it to print exactly how much I allocated, how many times it was called. You can do a lot of cool stuff with the dynamic tracers. So some of the benchmarking tools might integrate with some of that, and that would actually be pretty cool to see. That might inspire me to go look a little further afield. But yeah, there's a lot of stuff that you can find from the open source tools.
Yeah, great. Thank you.
With regard to your earlier question, Daniel, I installed Nextest if you want to see what it looks like. It wasn't very difficult to install. So this is what the next test command looks like. Where is this start? Yeah. So cargo next test run, and it looks like this. And then Beacon, I didn't have to do anything. It comes with a default job for next test on the hotkey N. So I just press N, and then that's what it looks like.
Oh, super easy. Nice. Thank you.
Yeah, it was actually, well, I had to install next test. That took a little while because I didn't use the pre-install binary, but other than that, it was pretty simple. I didn't actually have to figure out anything.
Yeah, that was pretty fast.
Yeah, next test is supposed to be up to 3 times faster than cargo test.
Interesting.
It does feel faster. I don't know if it's actually faster because I didn't time it or anything, but yeah, it felt faster.
Yeah. By the way, do you have a link to next test as well? Maybe Bacon.
I got the link in the Bacon docs, but yeah, I can find it.
Oh, here.
Yeah, just so that I can find
I
this.
can share it in the chat.
There we go. We got next test.
Oh, okay. Thank you.
Okay, cool. And there's Bacon. All right. So with that, we have 20 minutes left, and then I have a hard stop. I have to get everybody out of here. So yeah, any last minute questions, concerns, feedback?
Oh, Beacon also has a search option, so you can search for things in the output, which is not something I use very often, but something really nice to be aware of in case you actually have something you need to find.
Cool. All right. Then with that, I think that's pretty much it. Next month, I don't really have anything planned. So actually, we were in talks with Manning Publications, and they're still trying to get a hold of authors to maybe come here as speakers. So tentative plans there, but otherwise, if nothing happens, then it's a free talk. Or if anyone else has something that they want to talk about or present, then you know, feel free to reach out to me or reach out to Chester and let us know, and we can slot you in for next month. All right. That's it. Okay, everybody. Thanks for coming. And yeah, I'm going to just stop the recording here, and we'll just pack it up. So,
All right. Thanks a lot, everybody.
thank you all for coming.
Thank you.
Thanks.
Right, thanks.
Thanks for organizing this.
Bye.
Bye.